So welcome back. This is supposed to be lecture 10. Time passes awfully quickly, it seems to me, when you're staying home. I'm not quite sure where the time goes, but I'd like to come back after taking this little excursion into how to do model development. I want to come back to the base in-host model that we've been working on and try to finish that up today. Before we do that, I would like to have everyone go around the room and finish the updates. I think we still needed to hear from Devin, Brian, and Mercedes. And please do upload, even if your upload on the Canvas is just a single page Word document or something like that, please do file your report so that it can get graded, since I want to give you credit for the work you've been doing so far. And then, of course, there was the homework that was due today on how to write models. So I'd like to start by giving the floor over to you to do updates.
Yeah, I can go ahead.
Okay, great.
Mr. Glazier and Joshua have been helping a lot with this, but I did accidentally forget to save what I have. I took pictures of everything, but I just don't have it in a file right now. I can go ahead and share a screen to show what we have been working on. So basically, we've been working on this. My project is kind of like a predator-prey system for oncolytic viruses and cancer cells. So this is the general form that the equations take, and there's a bunch of different options for like the virus spread terms, which is the function g here, and the cancer growth terms, which is the function f here. And so what we worked on is basically solving these functions for different, I can't even remember how to explain it, but solving it and basically putting in different parameters and seeing where kind of equilibrium was found at. And so my next steps are kind of going to be making parameter scans to see what sort of parameters work best and stuff like that. That's about all.
Okay, I think if you can try to get those some of those different examples, you showed me some the other day. If you could get some of those examples running as time series, so you can see how the tumor grows and how the virus either controls the tumor or not in different situations, I think that would be very useful. So even before you do the full stability analysis, it's worth looking at just the time series and seeing how things go through. So that's fine. Mercedes, you want to give us an update?
Yeah, I can go through. So I am working on a modeling cancer tumors using radiation and immunotherapy. I met with Professor Amit, was that his name? And he was really helpful with kind of walking through the predator-prey model of the cancer tumors and just kind of like walking through it. And then I went back to my paper and realized that they kind of tried to stray away from the predator-prey model. And I'll go ahead and just share this Jupyter notebook that I've just been like writing notes onto. And my current thought is just to kind of use like their equations that they had for both just growth, cancer cell growth at both sites of the tumor, and then just the cell death for the non-immunogenic. So just basically competition for resources. And then they go on to, I believe it's this one. They kind of go on in the paper to continue with right after radiation, and I'm currently still trying to work on, is it not sharing? There it goes.
Are you sharing?
Is it sharing now?
Yeah, there we go.
Yeah. So this visual they had is kind of what I've been trying to work through. But basically, it's just showing like the way they did it, and the tumor on the left, number one, is their primary tumor, which starts out a little bit bigger. And when you go through the paper, you can see both at different doses of radiation and at different immunotherapies how both the radiated tumor gets affected and then the secondary tumor, which just has like an abscopal effect
Right.
from the radiation. So I was just trying to work on getting what happens just like growth on its own. And then I wrote down the equations they were using down here. And then this was the growth rate at each tumor site. And then this was the cell death just for competition. And then they used the total volume right here to use both from the cell death, from this amount of cancer cells, the death rate, and then I is the cancer cell dying due to the immunogenic response. And then these are just kind of like their basic parameters that they started out using for the different variables within the equation. So that's kind of where I'm at. And then this box right here was kind of just thoughts of what I originally thought as putting as inputs and getting outputs as. These two these two outputs are mentioned a little bit later in the paper once they explain what happens to each of the C, D, and I equations with the radiation. I'm just not there yet.
So do they actually give the equations that they use in the paper, or is it just the diagram?
Yeah, they give the equations. I can share that really quick too.
Mercedes, have you tried at least loading this as an antimony model?
No, not yet. That's what I was trying to get set up, but
okay, no problem. It's just that there's a couple of the syntax in the equations that I wonder if it's gonna work. But we can talk about it later.
Okay, I can set up a time. But here is the in the paper. This is where they started out with.
Right.
So
right, okay. Right, I get it. So I guess unfortunately you weren't able to make it last week. So the thing that we did last week in class was cover how to turn this kind of set of equations into antimony strings.
yeah, I started watching the lecture. I just haven't gotten all the way through it.
And so that's fine, but I think why don't you take a look at that, and then if you're having trouble converting these equations into antimony, Josh and I are happy to help you with it.
Sounds good.
Because again, it would be good if we can try to get. I'd like everybody to have something they can run, ideally as soon as possible, just so that we make sure that people are not stuck. That's the goal, is to try to make sure that nobody gets stuck. And so I'm happy to help. Okay. I guess, Brian, are you the last person to talk today?
Yeah, I think so. Give me 1 second. Okay. So I just made a small presentation. Let's take a look. So I basically tried to break down what I needed to address about the modeling project. I had a wide scope of things that I wanted to address, but I decided that by breaking it down into something perhaps very small, I could probably address it more easily, and that way I could address it on a larger scale. So these were some of the things I wanted to address in this presentation. So the essentially the statement that I wanted to go with was I wanted to create a Tellurium-based project that displays a wide array of projections for probable future scenarios for vaccine efficacy. And so basically, the thing that I wanted to do was try to emulate. Oops, I think I went the wrong way. I wanted to emulate something like this, where we had a sort of like a presentation of the data that has happened up to this point. And as you can see, this is a daily death scenario. And I wanted to be able to predict like a large display of vaccine efficacy scenarios for daily deaths in the future. So like maybe you would have like 10% efficacy up here and then like 90% down here somewhere. And I essentially, I also wanted to answer a couple of questions if I had the time to, which is if you had which is a pretty interesting one, if you had a vaccine with a given efficacy today versus a vaccine with a higher efficacy in 6 months, which one is better? And that's something that I thought was pretty interesting, because essentially what you could do is if you got this, if you got this this particular part in Tellurium coded up and working, you could essentially move this today slider to somewhere down here, where you would predict a 0% vaccine efficacy up to probably a certain point, like right over here, and then you would have the splay move out from here to see what would happen. And I think this is kind of an interesting question, especially with talks of a vaccine being all over the news nowadays. The approach, I just wrote down a couple of things I would like to tackle in sort of order. So first of all, I would take real world death data, similar to the one that Josh showed us in that one lecture, and try to implement it into Tellurium. Then write some Python to predict the death rate based on vaccine efficacy rates. So that would be this prediction right here. And then collapse all the efficacy rate graphs into one graph, so like this. And then finally answer the other stretch goal questions, which would be this question right here, this one specifically. And I drew a quick picture of what I would like it to work out to. If I get this, if I achieve this, this is the ultimate goal right here. This is hopefully what the end product looks like. And I just kind of tried to figure out what to do on Tellurium. I haven't figured it out yet, but this is sort of what I would use as the intake. And then you could basically put in whatever data set that you find, and it would start to splay out from this side forward. And I think that's the end of the presentation.
Great. Well, I think that's an interesting one. People are supposed to get put their projects up on NanoHub as the delivery of the project, and all of the projects would be things that I think people would use. This one might be of interest to a lot of people because they might be interested in trying to explore some of the issues with vaccines if we could get it up. Talking to Jeffrey Fox and the people in the NanoHub side, they're eager to have more people use it. So they said that if people get their projects up and can get 10 new users for your project, it's 10 people to try it, to try running the demo. They may be able to give some tiny prize like a hat or a scarf or a sweatshirt or something like that. I don't know how much of a motivation that is, but it's certainly possible. I was just looking at what you were talking about and thinking, I mean, in principle, you could imagine writing a, let's see if I know. It's not trivial, it winds up to, okay. I may have outsmarted myself here. I was trying to, no, it's not going to work. Okay, well, I don't seem to be able to draw all the way I want to be able to draw. I guess we could go over it another time. I mean, we started out with S. I don't know if you can see this.
I can see it.
IR model was our initial idea. And in our case, if we had a vaccination, we would have people going from S to the vaccinated category. And because the vaccine wouldn't last forever, we'd have people coming back to being susceptible. And because recovery doesn't give us perfect immunity, you'd have recovered going back to susceptible as well, like this. And then you'd have some kind of, principally you'd have births and deaths in this. But to begin with, you could simply say that the infected individuals can die with some rate, die like this. And one of the things that you could consider is this kind of base model would treat the population as a unit, and you could use this to ask the question, depending on how fast you vaccinate, how many lives do you save? We talked the other day about regulatory arrows versus transformation arrows. In our model here, the people who are infected infect others. So that would be a excitatory arrow between S and I like that. So this would be a base model structure that you could use. But what you could do is also you could imagine that this is one population where these people are, for example, people under the age of 60. And you could imagine another population, which would be older people. I guess if you're dead, you're dead, but we'll call it D1 and D2 anyway. And there's cross-infectivity. So the people who are infected here can infect the older group. The older people can infect the younger people, like that. And the probability of dying when you're infected will be higher for the older people than the younger people. And the time for which you're protected by the vaccine would be shorter for the older people, or the degree of protection would be less. If you want the vaccinated people to be able to get infected, then there'd be an extra arrow, which is even vaccinated people could become infected, although at a lower rate than for the unvaccinated. And in that case, if the vaccine is only moderately effective in older people, the gain here would be less than the gain there. And then you could ask the question, if you had two vaccines, both of which worked well in younger people, but only one of which worked well in older people, what would the total death rate be? And of course, you'll find that the vaccine that works better in older people probably is more useful in saving deaths, because relatively few young people die. And therefore, having better efficacy in older people might be important. The flip side of that is that, at least potentially, the it would take longer to develop a vaccine that works in older people as well as younger people. And so you might have more deaths before you start vaccinating. There's also a question, which is what fraction of people get vaccinated? So this vertical line here, this arrow from S to V1 and V2, is a question of how much vaccine is available, what's the public policy on it, and so on. So you could build a model like this that would look like a vaccination model, and then populate it with the data sets, like the R0 and the mu recovery time, these kinds of things that you have from the fits of the experiment, and then use this to predict the death rate. And so this is the kind of model structure you might be able to build. You could build something fancier, certainly. You could have births. Clearly, people aren't going to go from S1 to, they're not going to be born as over 60 years old, so B only comes in there. You might include deaths from other causes than COVID. You might include the fact that the younger people eventually become older, although that's at a fairly low rate if you cut it at 60 years old. But the basic model structure there would allow you to do quite a bit. And as I didn't send it around, I shared with you that paper. There was a news item in The Guardian by some British epidemiologists. And the reason that this came up was that, of course, there's a huge rush for the development of a vaccine. There was another news item a month or two ago in The Economist that said something to the effect, they did a rough calculation, and they said that speeding up the development of a vaccine by 6 months would be worth $1 trillion, because the economic damage of COVID is so great. That's, of course, assuming the vaccine works very well. And so, as you know, there are more than 100 vaccines in trials of various kinds. And presumably, as soon as there's any vaccine that seems to be relatively effective, that vaccine will get rolled out as fast as people can do it. The problem is that early vaccines tend to be not very effective, especially in the elderly. And they also tend to have more side effects. But once there's a vaccine out there, it's much more difficult to develop new vaccines. Because at the moment, doing a vaccine development trial is relatively easy because there's no vaccine. So you can easily compare people who are vaccinated with your trial vaccine to people who aren't and see which group gets sicker. Whereas once people are vaccinated, if the vaccine is reasonably effective, then you don't have the ability to test whether the new vaccine works because you don't have people who are unvaccinated to try. And giving a second vaccine on top of the first vaccine often doesn't work very well. And so what tends to happen is that once a vaccine is rolled out, they stick with it, even if it's not very good. And a classic example of that would be the tuberculosis vaccine. Tuberculosis vaccine has been around, I believe, since 1920. It's not used in the United States. It is used in France, for example. Everyone is pretty much vaccinated, at least they used to be, as children. But it's not used in the US. Its efficacy is not that wonderful, which is one argument for not using it. But because it was available, there was relatively little work that was done in developing better vaccines. And so the result is that at the moment, we don't have a good tuberculosis vaccine. There are other vaccines where there have, in fact, been a series of improvements. The classic example of that would be smallpox vaccination, which of course you don't have to worry about because smallpox is the one virus that seems to have been eliminated from the earth. But it was original smallpox vaccination was actually using live smallpox which is very dangerous. And they switched to cowpox, and then they modified it over the years. But the improvements of that vaccine literally took hundreds of years. Shingles vaccine has been improved. The one that I got 30 years ago has been replaced by a newer one. But typically the timescale for vaccine improvements is on the order of 30 years, not months. And so once a vaccine is rolled out, it tends to stick around for a very long time. And so then there's a question whether you might do better if you had waited longer and started with a different vaccine. One thing, ironically, if the world doesn't cooperate in vaccine development, the one good outcome of that, perhaps, if any, would be that different countries would have different vaccines. So the Russians will have a Russian vaccine, China will have a Chinese vaccine, the US will have an American vaccine, and then you'll be able to collect data on which of those national vaccines is better. At least in principle, you could do that. And then if you find out that one of them is much more effective than the others, you potentially could switch it out. And so effectively, the world, by balkanizing, is doing a set of experiments to compare the quality of the vaccines. But if there's a single vaccine that's rolled out worldwide and people use it, that makes it much, much more difficult to develop a better vaccine. And so that was the point of the article, and it's the kind of thing that one could address here. They were specifically worried about the efficacy of the vaccine in the elderly. There's a simple reason why they tend not to do the vaccine, the studies so much in older people, because they're most at risk. And so vaccination studies tend to be done in young, healthy adults. And they're the ones who tend to respond best to the vaccine, but they also don't tell you very much about how well it'll work when people get to be 70 years old. There does seem to be some data also from the Guardian, reported in the Guardian, that antibody lifetimes are pretty short. And so there's certainly a worry that any vaccine that is developed may not be effective for very long. And so that would, the efficacy of the vaccine versus time would affect this, rate of return from vaccinated to susceptible. And maybe also this rate here, rate at which vaccinated people actually get sick there. And the ratio and the efficacy in older individuals versus younger individuals would affect these numbers versus these numbers. So those are some of the things one might want to think about here. And again, I think you could build something that would be of really a lot of interest to people. You could explore some very important social problems. The way you laid it out, I think, was quite effective. Okay, does that everybody? Has anybody not? Kali, I think you spoke the first day, but you didn't, I don't think you uploaded anything to the website, to the Canvas, did you?
Yeah, I haven't uploaded anything yet. I should get on that.
Okay,
But I did present the first day.
You did, that's what I remembered, but it's 2 weeks ago, so I was trying to refresh my memory. And if you could upload something, then that way I can put the marks in for everybody. Okay, any other questions about that? I'll try to, I'm not going to have a formal assignment, but I will go around the room on a weekly basis from now till the end of the semester, asking how people are doing, just to help try to remind people that we need to keep moving. Okay, so just as a summary from last time, because some people missed the class, I know watching 3 hours of unedited videos is not very much fun, but I guess it's better than not having anything to refer to. The main point of that class last week, was to try to help people practice, and the homework was about practice, interconverting these diagrams, like the diagram of susceptible cells becoming early infected, late infected, and dying, producing virus. The virus decays and it infects other cells. A diagram like that. This kind of diagram on the top is what you see in a typical biology paper with no quantitative information. Below is that same diagram written in the form of chemical reactions, even though they're not chemical reactions. But the important thing in the bottom is that the rates are written. So the rates at which things happen are written down. And in general, unless I'm doing something like a sketch, the one I just drew on that screen share, I try to avoid having arrow diagrams without rates associated with them. But here we have something, this diagram here, the bottom one that I'm pointing to, is a fully defined mathematical model, except for the values of initial conditions. That turns into a set of ordinary differential equations. We have 1, 2, 3, 4, 5 variables. So we have 5 ordinary differential equations. We can write those differential equations here. The key thing to notice in the key thing to notice in these kind of ODEs is that when you have, for example, T cells becoming I1 cells like this, you'll see T cells disappearing here and the same cells reappearing here. So you have what's called a mass balance term, where the same term appears with a negative sign and then a positive sign. The I1 cells become I2 cells, so the I1s disappear and turn up in I2. The dying cells disappear and go into the dead cell category like that. And so you'll notice that if I added up dt by dt, di1 by dt, di2 by dt, and dd by dt, the sum of all of those together is 0, because I don't have any births, and I'm counting all the dead individuals as dead. I'm not throwing them out. On the other hand, the virus is off by itself. It's fundamentally acting as it's sourced from nowhere. I don't use up infected cells when I produce virus. And it disappears through clearance here, but it's not used up in infection. So the virus equation sits sort of independently. Its rate of production depends on the number of infected 2 cells here. Its clearance rate only depends on the amount of virus. And so you have a set of 4 equations that are mass interconversion, and then a virus equation that sits independently. And so last time we mainly practiced going back and forth between these 2 kinds of notation. And then we looked at how to write this as antimony strings. And I think for people like Mercedes or Brian, this is going to be important to practice this for everybody. But if you weren't in class last week in particular, it's perhaps be important, which is that antimony allows you always to write things as ordinary differential equations. You could write either this form arrow goes to t, which is equivalent to writing d by dt equals, or you could actually write t prime equals, for example, minus beta times b. That works too. Same thing. So I can write these ODEs directly if I want. And in that case, I'll have exactly as many lines in my antimony as I have ODEs. However, if I think about the arrow diagram, I can also have each arrow in my arrow diagram correspond to one arrow, one line in my antimony. And in this case, the way I've broken the equations down is a little bit different. So you'll notice this equation, I have minus beta VT plus beta VT, minus beta VT plus beta VT. Here I say T goes to I1. That corresponds exactly to this first arrow. And that's a rate beta VT. I only get one rate law, beta times V times T. This one law here gives me both this and this. So it's a little more compact to write that. On the other hand, for my virus rule, here my virus rule only took one line. Here, the creation of virus, one arrow, gives me one rate law. The destruction of virus, second arrow, gives me another. And so in this case, for each arrow, I get a line of antimony. In this case, for each equation, I get antimony. And it's really up to me and my convenience which way I want to write it, but I have to be consistent. And so it's important to learn how to go back and forth. And I think some people, it takes practice to get familiar with it. It's not something that one learns overnight. And so the exercises in the homework were designed to give you some practice doing that conversion, because in your projects, you'll need to be doing that repeatedly, going both in each of these pairs. You'll have to be able to go from diagram to ODE, from ODE to antimony, from antimony to ODE, ODE to diagram, and potentially directly from diagram to antimony and back. And so that was the point of that exercise. And really, that's the most important thing in the class so far, is to learn how to do that. So technical point of view. We also talked a little bit about some of the notational issues that you face. We talked about the difference between mass transformation and regulatory arrows. In this class, when we're not doing so much signaling in regulatory networks, some of the complexity of the arrows is not present. We do have to face the fact that different people use different kinds of arrows to mean the same thing, and sometimes the same arrow to mean different things. And so you have to watch your note. You have to be careful of that. It's a little bit like Chinese, where the same character can have different pronunciations and different meanings, and the same pronunciation can correspond to different characters, and the same meaning can correspond to different characters. And so it's a many-to-many mapping. It's not that there isn't some good, reasonable structure behind it, but it's not as simple as just a one-to-one correspondence. The other thing is that I mentioned that I will always try to write the rate laws over arrows when I write them. You'll find in some papers, and we found actually in one of the papers we were looking at with Josh, that there's a notational difference in chemistry in particular. It's assumed that whatever is on the left-hand side of the equation multiplies the thing over the arrow. So in other words, the rate at which susceptible cells become early infected cells is beta times V times T. But in many cases, you'll find that they will write just beta times V over the arrow. And you have to know that when you see beta times V, that really means that the rate is T times beta times V. How would you know? Well, one way is to think about what makes sense. Is the rate at which you produce I1 cells independent of the number of susceptible cells? Is that sensible? Well, if there were no susceptible cells, you would expect you can't produce any infected cells. But if T is 0, beta times V is independent of T, and therefore you'd have the number of T cells going negative. And so that suggests that there's a missing T. The other place that you'll see that a lot is in decay terms. So here the virus is decaying at a rate C. It's not reasonable to say that the disappearance of the virus is constant, independent of how much virus you have. Typically, you expect exponential decay, C times V. And so if you ever see a term arrow going to nothing, where there's no species amount on the rate, that means that you have to interpret this as C times V, and you have to go through everything. There's a little bit of an additional complication, though, with that, which is that particularly in this source term, the source term, you have nothing here, right? There is no source. So nothing times P times I2 is still P times I2. So this one term, this one rate, is the same between these two notations. Everything else is different. And again, this is one of these things that one has to develop some facility with. It's like, for that matter, I mentioned Chinese, but the fact that English, the way it's spelled and the way it's pronounced are not always simply related. There is a relationship, but it's not always completely possible to determine how a word is pronounced from the way it's spelled. And vice versa, the way it's pronounced may not tell you exactly how it's spelled. And so here you have to learn some rules about how to do this conversion. The other thing that is worth mentioning, and it's the reason we use this arrow notation in preference to just ODEs, is that if you have a set of ODEs, you can't in general determine the arrows that came from. For very simple situations, and most of the ones we'll work in class are simple enough that you can go backwards. But for complex regulatory networks in particular, you can't determine what the network was from the ordinary differential equations. Whereas the arrow diagrams always give you a unique set of ODEs. And so there's fundamentally more information in this picture of the arrows than there is in the ODEs that correspond to it. That may not seem important now, but if somebody's trying to interpret what you've done and understand what it means or use it or extend it, then being able to go backwards is important. Any questions about that so far? And this is review, but I wanted to spend a little bit of time on it because some people weren't able to attend class last week. And I wanted to go over the main ideas. Okay, the other thing that we did last week was a sort of a side note, which was a few people had looked at what are called delay differential equations, where suppose that the rate at which people get infected depends not on the amount of virus today, but suppose you're only measuring people when they get sick. So I go from susceptible to infected immediately in my model. In fact, that's not how it works, but I don't know about the I1 phase. And so I then would find that the rate at which people are getting infected depends not on the amount of number of infected people today, but on the number of infected people 5 days ago, which is when they were actually exposed. And so in that case, I might write approximation, simplification, which is that the rate at which people are getting infected depends, for example, on suppose X were the number of infected people a few days ago. And so the rate at which new people are becoming infected depends on the number of people who were infected at some previous time. And those kind of delay equations where the functions on the right-hand side of the ODEs don't depend on the current time, but on past time, are problematic for a whole host of reasons, mathematically in terms of their specification. And Antimony doesn't allow you, in general, to write delay equations. It always solves the right-hand side now, not at some past time. And one way of dealing with a simple equation like that is that you can write what's called a bucket brigade, where you create A goes to B goes to C goes to D goes to E goes to F, and then F disappears. And if you set your constants, rate constants right, you can get this kind of bucket brigade to do a pretty good approximation to a delay. And so here I've written a simple bucket brigade where I pass material from one to the next. And I have my K1 is my input, that would be X here in blue, and it's 0 for a while, and then it comes on, stays constant for a while, and then goes off. And I see that my F value here looks a lot like this initial value with a delay. Now it's not perfect. There's some rounding here at the bottom and the top corners, but it's not a bad approximation. For most purposes, it's good enough. Now exactly how you adjust the values of K to get different delays is a little tricky. And if people are doing delay equations, you can try this and play with it and see how it works. You can look it up. And I can work with you individually. But I did want to show you a simple way of getting delays. It's not very pretty because this one delay equation is now turned into 1, 2, 3, 4, 5, 6, 7, 8 equations. But there's a reason for that. Actually, a delay equation is fundamental, is formally an infinite dimensional equation. And therefore you need to do it perfectly, you'd actually need an infinite number of simultaneous ODEs to be able to describe it. So here we're truncating the ODEs stack to make it manageable. If I didn't care very much of how good the fit was, how sharp my edges were, I could have truncated it after 2 steps or 3 steps. The more steps I add to my stack, the sharper my boundaries will be at these corners. So if I care about the corners, then I have to make that sharper. If I don't care about the corners, I can make it shorter. And then we had gone to the adaptive immune system. We talked about the various components of the adaptive immune system, in particular, that the signal has to get in the form of antigen-presenting cells from the tissue to the lymph nodes. In the lymph nodes, the antigen-presenting cells and cytokines from the tissue lead to proliferation of T cells. Those T cells then come back to the tissue. And it's the delay due to the time it takes the antigen-presenting cells to get to the lymph nodes, and then for the T cells to proliferate in the lymph nodes, that leads to the delays in the adaptive immune response. If we didn't have that kind of architecture of the immune system with that delay built into it, we probably wouldn't get sick because our immune system would be able to handle pathogens immediately. Wouldn't take so long, or at least you'd only have the replicative delay, not the transit delay. But that's how our immune systems work. I guess it's an interesting philosophical question, perhaps, or epistemological question about why the immune system is structured that way. Why doesn't the immune system sit in the tissue itself? The answer is actually after you've been exposed to a disease, the second time you get it, your immune system responds much faster. But for new diseases, the first what's called primary infection, when you've never been exposed, there is this long delay. And there's not much you can do about it. The delay is about 7 or 8 days. And no treatment that we have can fix that. People try to short circuit it. So giving antibody therapies is one way of short circuiting it. In principle, I suppose one could give T cells, but the problem with T cells from somebody else is they're likely to go and attack your other tissues, not just the ones that have the virus. And then we also talked about phenomenological models, in particular this Hill function, which is a very flexible way of quantifying your ignorance when you know something is 0 at 0 and finite at infinity, and has a value of a half at some critical value. And by changing the value of n here, you can go from what's called a Michaelis form, this first one, to increasingly steep step functions, sigmoidal functions. And so this kind of functional form is used a lot in modeling. It also has two, a pair, it exists as a pair. There's an increasing Hill function, which has the variable on top and on the bottom. There's a decreasing Hill function that has 1 on the top and the variable on the bottom. And they're essentially mirror images of each other. The decreasing Hill function starts at 1 and goes to 0 at infinity. The increasing Hill function starts at 0 and goes to 1 at infinity. They're both 1/2 at the midpoint k. And so that's something that can be a useful mathematical formalism that we'll run into again. But we talked a little bit about this idea of trying to evaluate from reasoning about a problem what those functional forms should be. And we've talked about that a little bit just in terms of interpreting arrows. If you see an arrow diagram and it's not labeled, then you have to guess what the rate law should be. And one of the ways you can guess the rate law is to think about what happens in the case if I have A goes to B at rate f of A, and I don't know what f is. I have to ask myself the question, if I had a very small amount of A, what would this rate of conversion be? If I had a very large amount of A, what would this rate of conversion be? Usually I can guess. For example, if there's no A at all and A isn't allowed to go negative, then f of 0 better be 0. If I have a lot of A and there's some limit on the amount I can create a B at a given time, then f of A better saturate and better go to a finite value as A goes big. And I can ask the question about the limiting value at 0, the limiting value when A is very large. And once I've got the value, I can ask, does the functional form AF, is it have slope 0 at 0, finite slope, potentially it could be an infinite slope like that. If the value is non-zero, it could be infinitely decreasing slope as well. So there are many options. But you should systematically, when you're thinking about problems, if you don't have a functional form given to you, even if you do, you should ask the question, does the functional form make sense? And so, for example, Devin showed this set of 5 functional forms for the growth of a tumor, 5 functional forms for the rate of viral oncolytic virus proliferation. All of those functional forms were derived essentially from drawing diagrams like this and coming up with some mathematical function that had the shape they want. There isn't any ab initio information in those. Somebody drew a picture and said, I want this curve to look like this as a function. So here's the amount of cancer cells, and this is the growth rate. I want the number of this functional form to look like this, then wrote some function that had that shape. But the math came second. I drew the picture first and then came up with the math. So now finally we're back to where we were with people probably don't even remember this problem that we were working on 3 weeks ago. So we were taking our model that we showed of viral replication in the tissue, and we were beginning to add the immune system to it. And the first thing we were going to do was what we were calling cytokine production and decay. And the terminology is sort of unfortunate because the thing that we're going to call cytokine here represents a mixture of chemical signals, actual cytokines, and those antigen-presenting cells that are going to go to the lymph node and induce the production of T cells. But in the model that we're going to build, we're going to assume that once cells, and this comes back to some biology we talked about a couple of weeks ago. Perhaps I should have included a slide to remind us, but I didn't want to drag us through all of the biology slides another time. But I certainly encourage you to refresh your memory about them. We're going to assume that once the cells are infected, because I1 and I2 cells are infected, that they release a signal, which we're calling C, and that signal is going to be transmitted to the lymph nodes. And we're going to make a very simple hypothesis that the rate of production of signal, whatever it is, antigen-presenting cells or cytokine, is linear in the number of infected cells. That is the same kind of hypothesis we made about the production of virus by our I2 cells. And in both cases, it's not a wonderful approximation. It's the cells don't produce the same amount of signal. And they certainly don't produce the same amount of signal in time. Even one cell changes the amount of signal it produces in time. We're going to assume that there's no initial cytokine signal, that the tissue does not have what's called chronic inflammation. Chronic inflammation is simply that there are cytokines, what are called pro-inflammatory cytokines, that are always present. Most of us have some level of chronic inflammation. As we get older, it gets worse. It can cause all sorts of problems medically, but we're going to assume that that's not here in our model. Okay. And then once we've got the cytokine, we have to ask the question, what happens to it? And we're going to assume that it decays, like all biochemical molecules. And we have to assign a lifetime to it. And we're going to assume that it has a lifetime of about 12 hours. And remember, we're going to measure everything in days. And so that means that it's got a lifetime of a half a day, or to be more specific, it's a half a day corresponds to a decay rate, C sub C, of 2 per day. The cytokine level, the absolute amount, is just a placeholder. We're not going to, because it's some complex mixture of a variety of chemical and cellular signals. What we care about is the relative amount of it, not the absolute amount. And so we're going to set PC equal to 1. We're going to include the response in other terms rather than that. Okay. So let's, if we can, go back to our notebook. And this is a notebook that we had loaded up in a couple of weeks ago already. I loaded a new copy of it into the folder, the student materials folder. It's the same notebook we've been working on before. It's relabeled exercises for lecture 10 now, but why don't people try to upload that? So start up Tellurium, NanoHub Tellurium, and then upload the exercise notebook from the demos. And I'll give you a minute or two. The one you want to go to Actually, this exercise for lecture 10 has a lot of these demos, but we're going to go to the one here where it's labeled adaptive immune response, cytokine production and decay. I want you to go to that one. And this is the equation here. Let's see if it runs. Oops, so it runs. So why doesn't everybody simply go here, upload that, and run it and see what they get. And then we'll do the same thing that we've done before, which is I have the later versions of this already typed out, but as a learning exercise, I prefer people to start with this one that we have here and add the terms by hand, type them in by hand into the notebook. If you get stuck and you can't go forward, you can go down in the deck and pull the later models, but I think you'll learn more by implementing them yourself. Okay, so I'll give everybody a few minutes to find, to launch Tellurium, find the exercise, upload it, find your place in that exercise, which is cytokine production and decay, and run this, okay? And as usual, I will launch a poll. Let's see, polls. I'll launch a poll just when you're done getting things set up and you got it running, click done. And I'll wait until everybody has that working. And if anybody has any trouble getting things loaded or doesn't work, anything like that, just ask me or Josh and we'll do our best to help. Is the screen sharing okay for everybody? You can see things all right? I remember a couple of weeks ago, I was talking and talking and talking, and then Josh came in and said, by the way, you didn't share the screen. So that was embarrassing. So I want to make sure if I do something embarrassing like that, please tell me sooner rather than later. You can always laugh at me. It's fine to laugh at me. Last week, we had a kickoff meeting for this discussion group at National Institutes of Health on viral infections. And I was supposed to present the first 6 slides out of a 12-slide deck. And then my colleague in Florida was supposed to present the second 6. We had 75 people on the call, a lot of big names. And I don't know, I mean, maybe my internet has been poor and you've been unable to hear or see me repeatedly, but my experience, at least from my end, has been that my Zoom sessions have worked pretty well. But last Thursday, just as all these important people are hearing me present the title slide, I go to the second slide and my internet cut out. And it came back 5 minutes later. Fortunately, the screen share was not being done by me. It was being done by the administrator in Florida. And so the screen didn't go blank. I just disappeared. And Reinhardt, Professor Laubenbacher in Florida, was able to pick up and continue to talk without me until I came back on. But if there was, you know, there used to be a joke that Xerox machines had an emotion sensor, so that when you went to the Xerox machine to make a photocopy, if it was really important that you had to make those copies, say it was the report that you were going to give out to a bunch of people who were your boss or something like that, the machine would break. And so I was laughing at myself that the one time it really mattered that my Zoom connection stay up, my internet went out. People were assume that by now people are pretty used to that kind of thing. Okay, so everybody got this running. And the most important thing to notice is that nothing changed with regard to the cell population because we're creating this cytokine, but it's not doing anything. What is worth noticing here, and it's actually a defect of the model, is that if I plot in the second graph the viral load versus time, the virus, remember, comes up, peaks around 2 days, and then starts decreasing gradually. The cytokine comes up, peaks, and starts going down in 2 days as well. Why is that? Why is it not identical? Well, the viral production is P times I2. The cytokine production is PC times I1 plus I2. I1 and I2 have pretty similar responses, but they're not identical. I1 has this little peak early and then disappears. And so the result is that kicks up the cytokine level a little earlier than the viral level. But in general, we could have used the virus load instead of the cytokine load. It wouldn't make a big difference. So the approximation we've made here, the rate of cytokine production is PC I1 plus I2, is actually, we might as well not have put that in at all. We might as well just use the viral amount. We could have a more realistic, if we think that the cytokine really is representing the antigen-presenting cells, the production of antigen-presenting cells depends usually on the death rate of the cells. And so in that case, we should have had something like DI2 here. But again, that would still be proportional to I2. Wouldn't change things very much. So there's some details in this model that aren't really that useful. But they could be hooks for building a more elaborate or more detailed model. Okay. So we talked about a little bit about these antigen-presenting cells. The antigen-presenting cells are not modeled explicitly in the model we're going to build. It's a defect. But the thing that they do is they pick up fragments of dead cells in the tissue that have virus in them. When they do that, they change their form. As I mentioned, they crawl over to the lymph nodes. And when they're in the lymph node, they find T cells. And they touch the T cells. They form synapses with the T cells. And if the T cell happens to have a receptor on its surface that recognizes the epitope, the viral fragment that the antigen-presenting cell presents, that's why they're called antigen-presenting cells, then that T cell will begin to proliferate. And the answer is, how do you know, how come there's a T cell sitting in your lymph node that is able to recognize the virus? The answer is that that's purely by luck. Your body, when you're young, generates T cells that have random recognition sites. Those T cells sit there in your lymph nodes waiting around. If an antigen-presenting cell never shows up, those T cells sit there essentially for your whole lifetime, never doing anything. There's some new production of T cells, but fundamentally the repertory of possible T cells is limited. After you're a teenager, you don't produce a lot of new ones. And so you have to be lucky. And so one of the things the antigen-presenting cells do is they present lots of different fragments of the virus in the hope that at least one of those fragments will be one that some T cell that you already have can recognize. Again, if you think about it from an engineering or design point of view, it's an extremely inefficient system. Instead of having the T cell somehow sense the virus and be able to make something that will recognize it, you make a series of T cells that can recognize random things. You have one T cell that responds to people with pink hats. You have one T cell that responds to people with gray mustaches. You have one T cell that responds to people with funny glasses. And those T cells sit around, and if the antigen presenting cell comes by with essentially a photograph of somebody with a pink hat or funny glasses or a gray mustache, then that T cell activates. If the antigen presenting cell comes by with a picture that doesn't match any of the T cells repertory, nobody activates. In principle, of course, you could have you could have multiple T cells that respond as well. But the key thing is that how does the immune system know what viruses to prepare for? The answer is it doesn't. It prepares randomly for possibilities, and then you have to be lucky. You have to be lucky and have the right T cell in your repertoire. If you're immunosuppressed, you might not have one, in which case your body can't fight the virus. As you age, because of the variability of the T cells is determined primarily in your adolescence, childhood and adolescence. As you age, you lose diversity of T cells. And so elderly people are more likely to not have a T cell that's able to respond very well. So that's another reason why the immune response in the elderly may be weaker or less effective than in younger people. And I think I mentioned before, the organ that is primarily responsible for this is the thymus, which we're not going to model. The thymus is active but earlier in the process. Okay, so we're not modeling explicitly these antigen-presenting cells, although they're implicit in the C function that we have. They're going to come in, and we're going to assume that there are some T cells that respond. We don't really have any way in the kind of modeling we're doing to deal with the fact that there are a very large number of possible T cells, and there are a very large number of possible epitopes or antigens that the virus could present. Even the same virus molecule could be presented in different ways. The molecule has a shape. If it's sticking out, for example, the spike protein has that flange shape. It looks a little bit like a collarbone. If it's sticking out in one direction, the shape will be different from pointing in a different direction. And that might potentially excite different T cells. When you talk about polyclonal versus monoclonal antibodies, that's one of the things that they're addressing, is whether you recognize only one presentation of one molecule, or whether you have a bunch of different antibodies that recognize different presentations of different molecules. Some antibodies are more specific than others, and have a higher affinity and specificity as well. Okay, so we're going to think about now our antigen, our cytokine here, which really is an immune signal. And we're going to say that our signal, C, has to get to the lymph node. And this is a poor man's version of a delay equation. I showed you a 6 to 7 step approximation to do a delay equation. In this case, we're going to do just a single step, which is really not a very good approximation to a delay equation. But we're going to assume that it does take some amount of time for the signal to get from the tissue to the lymph node. And the rate at which that signal happens is given by rate constant C. The bigger Kc is, the faster the signal gets from the tissue to the lymph node. The units of Kc are what per day, as usual. In reality, it takes about 2 days for the antigen-presenting cells to get to the lymph node. So that means Kc would be about 1/2 per day. Once the antigen-presenting cells are in the lymph node, they don't stay there forever. They get washed away, they lose potency. And we're going to assume again that their lifetime in the lymph node is about 2 days. So the rate of clearance of the signal is about 1/2 per day. There are a couple of things that we've left out about the biology that a better model might include. One of them is that the antigen presenting cells themselves send out chemical signals. So they actually do send out cytokines themselves. And they amplify the signal that's produced by the infected cells. And the result of that, if I included it, was that the drawing. If I included it, is that no, it's not going to draw. All right, one more time. Not sure why not. Doesn't want to draw. Huh. That's interesting. It'll let me draw on the PowerPoint, but it won't let me draw on top of the browser window. Sorry about that. So if I had the antigen presenting cells relay the signal, what I would see is here's time. Here's the amount of cytokine C. It would come up the way I show it here. And then instead of turning over here, it would go up even more. So we'd have more of it. And the shape would be different. So then the virus curve and the cytokine signal curve would be different. For the moment, that's going to be something we'll leave in the future. That's something to think about. Okay. So we're now going to add equations. We've got our equation for producing our cytokine and antigen presenting cell signal in the tissue. Now we have to get it to the lymph node. And so we're going to have a transport term, Kc times C, going from one to the other. And then a clearance term, Cl goes to nothing for HCl times Cl. And so that'll give us a mass balance term. That's the transport of these cells and signal from one compartment to the other, and then the loss of this to nothing. So what I'd like you to do now is add, and this can be practice. I've got it typed here, but you can try it on your own, maybe without reading it first. We've written this equation here already. I'd like you to write the antimony to implement that, and then run that and see what happens. Okay. Again, in green, I've shown what my answer is, but I think as an exercise, it's better if you try to look at this arrow diagram and then type the antimony that would correspond to it. So that's our next exercise. And as usual, I'll start the polling just to give people time to try it out. And you can let me know when you're ready. And if you finish a little bit ahead of your classmates, one thing you could do would be to change the value of these two constants and see what happens. You could make the time it takes the signal to get from the tissue to the lymph node longer or shorter and see what happens. Or you could make the time it takes that the signal stays present in the lymph node longer or shorter and see what happens. And the one thing, of course, you'll see when you do this is it doesn't change the amount of infection or anything else, because at the moment we're sending the signal to the lymph node, but we're not doing anything with it. Okay, so if I come to here, I could type E8, C goes to CL at a rate KC times C at a cytokine transport. And I could then have E9, which is the clearance. CL goes to nothing at a rate CCL times CL. Then I have to give the initial value for CL, which is 0. And parameter values as well. Here I said that the values should be 1/2, and I've actually typed them in as 1. So let's see what I have here. Here they're correctly 1/2. So let's see what happens when we run that. What did people get? Let's see what they got. So if I look at my cytokine level in the lymph node, which is orange here, you'll notice that the amount of cytokine in the tissue is very similar to that in the lymph node. Modulo, it's a little more rounded in the lymph node. And you'll notice there's also a delay. And the delay here is short. I wanted a delay of 2 days. It's shorter than that. So if I wanted to really make my delay bigger, I'd have to make this KC smaller. So why don't we try that? What if we make KC much smaller? That's the transit time. The rate of transmission. So make it 0.25 instead of 0.5. What happens? Delay goes up. Not so much. What I see instead is that I get a lower value and it's a little rounder. As I mentioned, using a single step is not a very good way of implementing a delay. Suppose I make it actually so it should take 10 days. See a little bit bigger delay, but not a lot. So this model actually isn't that great in terms of the time it takes for my signal to get to the lymph node. It's a little fast. Okay. And the exercise that I wanted to play with was a little bit, what happens when you change the time to the antigen presenting cells take to cut the lymph node, which is what I've just done. What if you made it bigger? What if you made them faster? So I had my KC here. I started out with it as a half. Let's make it bigger. Let's make it 2 instead of a half. Try that and see what happens. That does shorten the delay. So what I'm seeing here is that for values of KC bigger than a half, the delay is very short, but making it smaller than a half doesn't make a big difference. If I wanted to make the delay longer, I'd have to stack those intermediates that I showed you in the delay equation. Okay. So maybe now is a good time. Now we have to think about T cell proliferation. So maybe now is a good time to take a break. So let's take a 5-minute break. Have people come back at 6:30, and then we'll start thinking about the T cells in the lymph node. Okay? Is that all right for people? Is this a good time to take a break? No wild enthusiasm, but also no. Okay, fine.
Yeah.
One person says yes. In my view, that's enough. Okay, good. So we'll start. We'll take a 5-minute break here, and then I'll see you back in a couple of minutes. So now that we've got our signal to the lymph node, we're going to imagine our antigen presenting cell going around finding T cells, which are sitting there, quiescent T cells. And the antigen presenting cell will go to each T cell, it'll show it a picture of the virus. And if the T cell is primed to respond to that particular picture, it will start replicating itself. And it'll do that through the standard cell cycle process. And in reality, we don't really know how many T cells they're sitting there waiting to be turned on. It's going to vary from person to person. What we do know is that the rate at which the T cells replicate is about 1 per day. And we're going to assume that the signal from the antigen presenting cell, each unit of signal activates a different initial T cell. And so what we're going to have is we're going to have exponential growth because we're going to have T cell divide and then divide again and then divide again and divide again. So that means that the rate of T cell production, is going to be T cell turned on by the antigen presenting cell, and then it replicates. And so that means that the basic rule is that each T cell, once it's activated, replicates with a rate RE, and that rate is going to be proportional to the number of activated T cells. You're going to have a rate at which you create new activated T cells, which is the rate at which antigen is presented to them, which is going to depend on CL. And there's going to be some saturation because your lymph nodes can only accommodate a finite number of T cells. And so if you have too many T cells that are trying to replicate, the replication rate goes down, and that is with this decaying Michaelis term that looks like this, where this is EL. So there's rather a lot going on here. This is probably the main piece of the immune model. You could ask, why are there all these pieces? Well, if there's no signal to the immune system in the first place, the number of replicating immune cells is 0. And so you need to have some source term that's creating cells to replicate. Once the cells replicate, the fact that they replicate exponentially means that once you've started this process, the number of immune cells is dominated by the exponential growth. And so you have to have this term here, which is the exponential growth. That represents this arrow here. And then if you don't saturate that, the number of immune cells will go to infinity and the model will break. And so we have to have something that respects that there is a finite number of immune cells that you can accommodate in the lymph node. In reality, your lymph nodes do swell up during infection as the T cells are produced. So that's where part of where the concept of inflammation comes from, swollen lymph node in response to an infection. Now, the particular parameters that we're going to use here are pulled out of the air, except for the rate of replication. We're going to say that each immune cell can reproduce once per day, and there is a bit of a bound on cellular replication. In humans, about the fastest that our cells can replicate is 12 hours, so twice per day. Most of our cells don't replicate that fast. A typical replication time could be 2 days. Immune cells replicate a little faster because they need to respond quickly to signals. And so a 1 day cycle time isn't a bad approximation. You could assume a half-day cycle time. We could explore that. Okay. What's more problematic is this Michaelis constant, the saturation constant, KEL. All of these numbers basically are not scaled to anything. So in a real tissue, we know how many cells there are. In the lymph node, we're not trying to say that there are actually X number of cells. And so what really matters is relative numbers rather than absolute numbers. But we have to have some scaling. In this model, we've picked a scale factor of 1,000 T cells of a particular type. From the point of view of the model, we could make that number anything and compensate elsewhere. And so that's the base model there. And so this is the key idea, that we're going to have this production of immune cells. First, again, this first term is the chemokine signal and the antigen presenting cells taking cells that were initially sitting in the lymph node in a passive state, in a quiescent state, and kicking them into cell cycle. And then the replication of those cells, which is exponential, saturated by a maximum capacity of the lymph node. There's a lot of grounds for thinking about different functional forms for these kinds of equations. And we could go back to the kind of argument we made before about what they should be. But this is a simple set of approximations. So why don't you actually, instead of by jumping to that, why don't we do the next exercise? The next exercise would be to take our our CL signal now and implement this equation in the form of another set of antimony. So I probably should have said that this was the exercise, but I'll do it. So the exercise now is to add DEL dt, effectively the number of immune cells in the lymph node, to your basic antimony model. Okay, so I'd like you to go into your ODEs here, or to your antimony, and add the terms. And again, this is practice of converting ODEs or diagrams into antimony strings and making sure they work. So you have here del dt is equal to, we're only creating these, so it's going to be nothing goes to EL semicolon, then the rate law. So why doesn't everybody try that and implement that? If you have any questions about that, let me know. Give it a try. And I'll try to be a little more lively and speak a little bit louder, but I seem to be losing my voice. I must have been talking too much today. And so I'm doing the best I can to be audible. So I appreciate your patience. If you've got this going already, I would suggest exploring what happens when you change REL here. You could make it 2, which would be a cell cycle time of 12 hours, or 1/2, which would be a cell cycle time of 2 days. What happens to the number of EL cells in the system? The other one that's going to be relevant would be PEL. That'll tell you how fast the system responds initially to the signal. And then KEL, which will determine the maximum number of immune cells that you get. So if I were going to do this, I'll start. People should keep going if they're doing it, but E10 on nothing goes to EL, semicolon, EL times CL plus REL times L. And then you'd have to type the additional parameter values down here. There's a practical mathematical reason why we need this source term PEL times CL, which is if we just had the replication term and we started with EL equal to 0, then we'd never get any ELs. So we have to have a source term that's not proportional to EL to get the thing started. So that's a mathematical justification for the form.
James, question about that. Because right, that's the way we solve that problem. But we could have solved it differently too. We could have started with a non-zero initial condition of T cells, and then that have the scale at which they migrate to the tissue to be very slow relative to the replication rate.
Yeah, that would work. There are a lot of options here. Part of the reason that this is becoming problematic is that we have in reality. Well, the reality is probably much more complicated than what I'll draw, but the reality could be that there's some kind of quiescent T cells, and those quiescent T cells become proliferating T cells, and the rate of that is determined by the cytokine in the lymph node. And then once we have the proliferating T cells, they replicate. And so the reason we have this term here sitting like that is that we didn't explicitly represent the fact that they're quiescent T cells sitting there waiting to be activated. And so if I had written out that extra term to represent the reality that those cells exist before we start, then I wouldn't have this problem.
Correct.
So that's a good point. Okay. Okay. So this was the example that I gave. And now we're going to have a new cell type population. I'm going to do a Julia Child, which is that I have these done already, so you get to see the result. And now I have my T cells. I start out with no T cells. Once the CL value in orange begins to go up, I get initially very rapid production of T cells. And then as that saturation term kicks in, the number saturates. Notice the number of T cells is going up to a very large number. It's 1 e to the 10th. So that saturation term isn't doing very much. Basically, the number of T cells is running away, which is probably not a tremendously good approximation. Although in reality, the T cells are produced rapidly and they go, and the number is large. I could play with this a little bit if let's see what would happen if I made the time it takes my signal, my KC signal, longer. That would make this 1/2 something smaller. Let's try 0.1. So now, what happens? Not a lot. It takes a little bit longer to get started for my T cells to get started. And the final number is a lot smaller. It was 10 to the 11th before. Now it's 10 to the 9th. So I've reduced the number of T cells by 100 at day 10. In reality, you'd never get that many T cells. What else could we do with this kind of problem? Well, we could look at the saturation value. I said that the rate saturates at 1 e to the 3. I make the saturation smaller, 1 e to the 2. I don't change the shape, but I've reduced the final number by a factor of 10. What else could I do that would change the rate? The one that probably matters the most is the replication time, REL. Here, I've said they reproduce once per day. If I make them reproduce twice per day, make that a 2. Doesn't seem to do much, does it? Not really. Doesn't change much. But if I make it take 2 days to reproduce, let's see, REL, that would be 0.5. If I slow down the replication, I reduce the number of T cells another factor of 10. Well, the shape of the curve is improved. Okay. So now I have a situation in which, in reality, these immune cells shouldn't just be accumulating. They either should have a finite lifetime or get moved somewhere else. But now I have a situation, and again, there isn't really that simple a way to model what's happening because there are a lot of steps. I have a signal that starts in the tissue. It has to get to the lymph node. Once it's in the lymph node, it has to stimulate these T cells to proliferate. So we've gotten that far. And once the T cells have proliferated, we have to get them back. We have to get them back to the tissue. And so now we need to transport the T cells that we produced in the lymph node back to the tissue. Because they're active in the tissue. Now, we said that the transport from the antigen-presenting cells from the tissue to the lymph node took a couple of days. Going the other direction, the cells go through the blood, not through the lymphatic system, at least primarily not through the lymphatic system. And that transport is much faster. That transport's in the order of hours rather than days. And so the back transport is pretty quick. Once the T cells get into the tissue, they're going to start killing infected cells. We're not going to put that in yet. But they also have a finite lifetime in the tissue. Exactly how long the T cells stay in the tissue is variable. There always are some T cells in your tissues, sentinel T cells. But we're going to assume that the cells take about 2 days to get back. That's actually not right. They're faster than that. So we're basically assuming they're going back through the lymphatic system. And then once they're there, they stick around for about a day. And so that means we're going to have our EL goes back to immune cells in the lymphatic, in the tissue. So the EL cells get transported back to the tissue, and then those immune cells eventually disappear. There's a typo in this picture. It shouldn't be here. And so we are going to have a rate of transport, KE, that takes the immune cells in the lymphatic system to the tissue, and then a rate DE, which eliminates those immune cells from the tissue. And we're going to start out with KE is a half per day, so that means more or less 2 days to get back. And DE is 1 per day. They stick around for about a day. So the next little exercise is to implement this. So you have now these additional 2 arrows, this one and this one. Why don't you try putting that, or this one ODE, why don't you try putting that into your antimony and see what happens. If you've gotten through this exercise quickly, why don't you try changing these 2 rates and see what the effect is on your results. notice that this first rate, KE goes to L, will affect two things. It'll affect the number of T cells in the lymph node because the T cells are going out of the lymph node. And it'll affect the number of T cells in the tissue. This decay rate, DE, will only affect the number of T cells in the tissue. And again, that shouldn't be there. We were talking about mass balance term. Here's another mass balance term, this one and this one balanced. And again, I think that when you do start doing these things, it feels it may feel, maybe not, but for some people it may feel sort of alien. But you'll see we're doing the same thing again and again. And I hope one of the reasons I'm walking you through all these steps is that I'm hoping that with the practice you get from repeating these things in slight variations of each other, that then when you look at a problem in a book or in a journal article, and you want to implement it as antimony, it gets more automatic, or at least easy, more comfortable to do this translation. So here were my versions of this. Again, so far, the immune cells and all of this thing that we've been doing aren't changing our infected tissue at all. And so everything we've done so far hasn't had any effect on the infection or on the amount of virus. But now I see something that's a little bit interesting. My number of immune cells in the lymph node goes up, I expect, but then it turns over and starts coming down again. The number of immune cells in my tissue stays low up till about day 4. Then it gradually comes up, it peaks around day 7, and then starts going down again. And that's beginning to be a little bit more realistic. The one thing that's not realistic is that the time when I'm first getting T cells back into the tissue is a little bit early. If I wanted to make this a better model, I can't, again, I don't know why it won't let me draw on this side. But if I wanted to make this a better model, my orange curve really should stay low till about day 4. So the T cell availability is a little bit fast. But the basic shape of what's happening is reasonable. Did anybody try changing KE or DE and seeing what happens? If I make DE bigger, what's going to happen? Why don't people try making DE 5? That would mean that the immune cells only stick around about 4 hours, 5 hours in the tissue instead of the whole day. What happens? You have to remember maybe what, here it's 3.5, 10 to the 9th at the top. Let's try making DE bigger, making the clearance rate bigger.
What I noticed, I think the most obvious thing that stuck out to me was that in the final T cells graph, the orange curve representing E, I think, is significantly dampened.
So yeah, absolutely. If I make that number bigger, it flattens out the T cell curve a lot. If I go back, what about changing the time scale? What about changing the time scale for the transport, KE? If I make that faster, which it should be probably, it should be a number, it should take a few hours instead of 2 days to get back. If I make that number faster, what happens? Well, now my orange curve shoots up earlier and it peaks at a much higher value. It peaks about twice the value it had before. So in this case, I cheated a little bit. I picked numbers that gave results that I knew were right. But I didn't have a justification for the parameter values I picked. What else could we do? We could try changing REL, that was the replication rate of our T cells. What if we made it slower? As you get older, those cells replicate more slowly. So make it take 2 days to replicate my T cell. That slows down the T cell response, and it also reduces the maximum amplitude quite a bit. What else could you play with? Well, you could play with the rate at which the initial T cells are created by the immune signal. That's another thing that happens as you get older. When you age, you have fewer quiescent T cells to turn on, and their response is a little bit weaker. So that would make PEL smaller. Here it's 1 10 to the minus 4. Let's make it 10 times smaller, 1 10 to the minus 5. Did that actually do anything at all? I'm not sure. Doesn't look like it did much, did it? So sometimes some of the parameters may not be doing what we think they're doing. Okay. But it made some difference. Here it's 3.5 10 to the 9th. Here it's 1.75 10 to the 9th. So reduce the number of T cells by a factor of 2. I would have expected a bigger effect. Okay. After all of that, we now actually have to think about what the T cells do in the tissue. And you could ask the question, why does the immune system need this very complicated set of mechanisms? And the reason the immune system has to have this very complicated set of mechanisms is that what the T cells are going to do once they come back to the tissue is that they're going to look around for cells that are infected. And host cells, as your body cells that have the virus in them, are going to have some amount of virus on their surface. And the T cell will look for that virus because it has what's called, well, it has actually an antibody, essentially here, an antibody that's going to look for the antigen that it was trained that the T cell responds to. And if the T cell finds that viral marker poking out of the tissue, the cell in the tissue, it's going to form a synapse with it and kill it. It's a little bit more complicated than that because there's a set of major histocompatibility recognition that try to prevent the T cells from killing normal cells when they're not infected. And that's a whole set of details we're not going to model. They're very interesting. If you want to do a complete model of the immune system, you need to include this. There's always a problem and this is a problem that's true with infections, and it's also true with cancer. It's even more true with cancer, which is that you want the immune system to kill cells that are misbehaving in some way, whether that's a cancerous cell or a cell that has a virus or bacterium in it. But you also don't want your immune system to go around killing normal tissue. And the problem is, especially with cancer, that the molecular signatures of a cancer cell versus a normal cell are very weak. And so the ability to discriminate between a cell that is normal, that the T cell shouldn't kill, and a cell that is defective because it's cancerous or because it's infected is a pretty weak signal. And the consequences of the T cells not killing the cells they need to are that you die of the bacterium, the virus, which proliferates in an uncontrolled way, or that the cancer is able to proliferate. On the other hand, the consequence of the T cells killing cells they shouldn't be killing are autoimmune diseases like arthritis and many others, and they can be lethal. And so the balance between T cell activation and T cell suppression is very complicated because you need to respond very hard to things that are non-self that should be gotten rid of. And you need to be very careful that you don't kill anything that you shouldn't. And if you have millions or hundreds of millions of T cells moving around and tens of billions of normal cells, even small mistakes have big consequences. And so the fact that the system is able to avoid autoimmune responses for the most part, and to get rid of the pathogens for the most part, is pretty remarkable. And so there's a very elaborate dance that is done between T cells and the cells they're going to kill. There are multiple molecules that are used to signal back and forth so that the T cell is able to make a definitive decision about whether it should or shouldn't kill the target cell. These major histocompatibility complex molecules are part of that dance. And we're not going to go into the details here. Once the T cell's decided that it's attached itself to an infected cell, it can kill the target cell in a variety of ways. There are things like proteases, which permeabilize the cell membrane and basically cause the contents of the target cell to leak out. There are reactive oxygen species that can be released into the target cell and kill it. There are explicit receptors on the surface of the target cell that can be activated by the T cells and cause programmed cell death. The protease mechanisms are not programmed cell death. They're lytic, usually lytic cell killing. The reactive oxygen species can go either way. And the T cells can also, and some of the other immune cells can also release molecules that kill not only their target that they're attached to, but neighboring cells as well. Mercedes was talking, I think, about the secondary killing of immune response when you have radiation. And that's one of the kinds of what's called bystander effect, where the killing of a cell leads to the death of neighboring cells as well. That can be very useful because the T cells have a limited bandwidth. It takes typically a T cell 40 minutes to kill its target, give or take. And that means that if you have a lot of infected cells and the virus is spreading rapidly, you'd need a lot of T cells to control it, maybe more than you can accommodate. And so for the T cell to be able to kill not only one cell, but multiple cells at the same time, makes the killing process much more efficient. The downside of it is that you're killing indiscriminately. You're not only killing the cell you've identified as infected, but you're killing the neighboring cells. Some of those cells might be infected, some might not. And so when you have cytokine storm, where you have large-scale tissue damage, one of the reasons you're getting that is that the T cells are killing not only the infected cells, but also non-infected cells. And so that's typical of an autoimmune problem. The other thing that can happen, which we're not going to talk about so much, is that the activated immune cells themselves can relay cytokine signals of various kinds. And so there's an amplification mechanism where the cytokine signal that we have here is enhanced by the immune cells in the tissue. We're not including that in this model. These are all, again, Sam's slides. One of the things that, of course, again, if the immune system worked perfectly, and all of these defense mechanisms work perfectly, then you might get a very mild infection, but in general, you wouldn't get sick from the virus. The immune system would control it. The fact that the virus survives well enough to propagate and make us sick means that the virus is defeating various aspects of the immune response. And this slide talks about some of the things that viruses can do to inhibit being killed by immune cells. And there are quite a few. So one of the things that they can do is persuade the immune cell that they're not actually infected. That would be the first one or two. They can reduce the amount of antigen that the cell produces on its surface, so it makes it harder to recognize. They can either send a signal to the immune cell saying, "I'm really okay," which is positive, the inhibitory part of the response, or they can reduce the signal to the immune cell saying, "I'm sick." It's the second one. Some viruses can infect immune cells directly. Of course, HIV is famous for infecting immune cells, but there's some evidence that SARS-CoV-2 can also infect some immune cells. What happens when those cells are infected is not obvious. In some cases, it may kill the immune cells and reduce the immune response. In other cases, the immune cells may still continue to function. And so there are a whole variety of arms races, as usual, between the virus and the immune system. As I mentioned, the immune response itself works by killing host cells. In general, it's not 100% true because most things in biology have counterexamples. But in general, once a cell in your body is infected with a virus, that cell will die from the virus. And so the only thing that your body can do to get rid of the virus is to prevent other cells from being infected. And to do that, it's got to kill the cells that are infected so they don't produce more virus. And so the immune response is in itself destructive. The reason they're called cytotoxic T cells, for example, is because they're killing normal cells in your body. They're killing normal cells that are infected, but these are nevertheless normal cells in the body. If I kill too many cells in the tissue will die. And my lungs, if I kill a lot of the epithelial cells in my lungs, the lining of my lungs will disappear, and the fluid in my body will leak into my lungs, and I'll get pneumonia. And so there's a complicated balance, which is that if I kill too many cells in my tissue, I'm going to die from the immune response itself. In sepsis, that's exactly what happens. And so there are all sorts, and I'm not going into the details of all the different kinds of immune cells. There are multiple kinds. The ones that you run into the most frequently are CD8 plus T cells, which are the main ones we're modeling here. CD4 plus T cells, which are mainly regulatory in most cases, rather than doing the killing themselves. And then B cells, which are mainly responsible for antibody production. All of these can, in principle, damage tissues. We'll focus on the CD8 plus T cells in our model, which are the ones that are primarily killing the infected cells in our case. Okay, so now we're going to finally close our loop. After a lot of discussion, we're finally going to have our immune system do something. Because so far it hasn't done anything to our initial. If I look back here, my picture at the top, which was the production of infected cells and virus, didn't change. I put in all these extra models and terms and nothing's happened. And the reason for all of this is we've had to go through all the steps of getting the immune signal to the lymph node, having the lymph node produce immune cells, having the immune cells come back to the tissue. And now the immune cells are going to do something in the tissue, namely kill infected cells. And we have to make a little bit of an assumption about how that's going to happen. In particular, for example, the immune cells might kill both the early infected and the late infected cells. The early infected cells, however, haven't yet started producing virus on their surface. And so while it's possible that some T cells could recognize that, they're going to have a harder time. And so our base model will assume that we can only kill the late infected cells, the ones that are producing virus. We also have to have some idea of the rate at which the T cells are going to kill their targets. And that's probably the single most problematic thing in this whole model. In reality, there's a lot that has to happen for a T cell to kill its target. In the first place, the T cell has to come from the lymph node, get into the tissue. That takes some amount of time, although since they're transported in the blood, and since the lung is a thin tissue, the T cells are able to get into the tissue pretty easily. Once they're in the tissue, they have to find the infected cells. And the T cells will crawl around randomly, exploring their environment. They'll diffuse in the tissue. There also are chemical signals which are called chemokines, which are produced by infected cells. And the T cells will follow gradients of chemokines to find regions in which there's a high rate of infection. And so that's directed movement as well as random movement. If the infected cells are far apart from each other, it may take a significant amount of time for a T cell that's just killed a cell over here to move to another location and kill additional infected cells. T cells crawl around pretty fast, though. So it does, unless you have patches that are far apart from each other, the T cells move pretty fast within the tissue. Once the T cell has found a target cell, it has to go through that elaborate chemical dance of synapsing that I described in some of the earlier slides before it's actually able to kill the target cell. And that process, again, takes somewhere on the order of 40 minutes, maybe 20 minutes, sometimes an hour. It's also possible for some cells to need multiple T cells to attach to them at once to kill them. But it's also possible for one T cell to touch multiple cells and kill them simultaneously, making it a little bit hard to estimate how much they can kill. But there is a limit. If I had an infected tissue with lots and lots of infected cells and only a few T cells, I can't kill more than that number of T cells times about 30 per day. And so the simplest thing that I could write down would be the simplest thing that I would write down is that the number of target cells that I kill would be something like DEI2, the rate of killing of target cells by immune cells, times the number of target cells, I2, times the number of T cells, E. That would be what's called mass action. This has the right property that if there are no infected cells, I don't kill anything. If I have no immune cells, I don't kill anything. So for small numbers of immune cells and infected cells, this makes sense. But if I think about the opposite limit, if I think about if I have a lot of I2s, a lot of infected cells and a small number of immune cells, the most I should be able to kill per day would be something like, I said 40, so something like 30 times E. So this number should never go above 30 times E. And that means I have to have a saturation term where if the number of I2 cells is a lot more than my E, the rate of killing doesn't keep going up. Similarly, if I have only a few infected cells and they're very far apart, it takes a long time for my immune cell to find its way from one infected cell to the next. And in that case, if I2 is small and E is large, the rate of killing, as I increase the number of E's, my rate of killing doesn't keep going up. So I have to have a saturation term, a Michaelis term, which is saturated both in the number of immune cells and in the number of infected cells. And the exact form of this is not obvious, and the form that's picked here may not be right. But the main idea here is that if I have a small number of E and I2, I should get DEI2 times E times I2. This is bilinear. It goes to 0 when E goes to 0 and when I2 goes to 0. If E is very much bigger than I2, I want this to be a constant that's proportional to I2. If I2 is very much bigger than E, I want this to be proportional to E. And this particular functional form has those properties.
James, can you explain that again? With the limits. Explain. Can you explain it with the limits?
Okay. So if the naive thing to do would be to say that I have, just like an infection model, the one we started with, an SIR model, that when I have an immune cell encounter an I2 cell, it kills it. In which case my rate of killing would be DEI2 times the number of immune cells times the number of infected cells. And this has the right behavior in the sense that if I have no immune cells, I don't kill anything. If E is 0, this rate of killing is 0. And similarly, if I have no infected cells and I have immune cells, the rate of killing is 0. This is assuming my immune cells aren't killing anything except the I2 cells, and that the I2 cells are only killed by the immune cells. So the limit is E goes to 0. This is 0, which I want. And the limit is I2 goes to 0. This is 0, which I want. The problem is when E and I2 are large. And if they're both large, it's less of a problem. The problem is if I have a lot of I2s and only a few E's. Suppose I only had one immune cell in my tissue moving around. In this bilinear form, as I increase I2, the rate of killing goes up linearly in I2. However, I know that one immune cell can't kill more than 30 I2s per day. And so what I want if this is the number of I2s, and this is my killing rate, DEI2 times E times I2 is a straight line. Keeps increasing. In reality, I know that that number can't be more than 30. I better write it over here. Can't be more than 30. So I can't have this increase linearly. I need something that starts linear and saturates like that. That functional form is what's called a Michaelis form. And I would expect that to be saturated by I2. So I would expect to see something that looks like this. KEI over KEI plus I2. That'll have the property that when I2 gets big, this goes down and cancels this I2 here. So that gives me saturation. If I have a limited number of E's, my killing rate can't go too big. Similarly, if I have a lot of E's and very few I2s, so here's one infected cell, here's another infected cell. It takes time for my E that's just killed this guy to find its way over here to kill this one. And so adding additional E cells doesn't speed things up that much because I'm determined by how long it takes to get from one place to another. And so the same thing happens here, which is that if I have too many I2s versus E, then I want my rate to be limited. And so here, excuse me, I said that backwards. If I have too many E's compared to I2, I want my rate to be limited. And so I need this E in the denominator. So if E is very large, then this E cancels this E here, and my rate is independent of E. So this equation has the property that if E is very large, my rate is independent of E. If I2 is very large, my rate is independent of I2. If E and I2 are both small, my rate is linearly increasing in I2 and E. And so the limits make some sense. The exact form of the limits and whether there should be prefactors in the denominator is something that's not considered here. In particular, there's no particular reason these should combine in the same scale factors. But the basic idea that the rate of killing has to saturate both as I increase E and as I increase I2 has to be true. And so that's fundamentally the most difficult argument here. And if you look in the literature, people have come up with all sorts of different functional forms for this. In reality, this is determined by the spatial organization of the tissue. It's not determined in this simple way. And so there's been a lot of argument and debate about functional forms for this killing factor. For now, we're going to just assume that this one is right, whether it is or not. And so the next exercise, and we're going to be almost at the end of the lecture in a few minutes. Well, actually, we've got half an hour, but we're getting close to the end of the model. The next exercise would then be to add this to your model. And so let's just look back over here. What would be happening here is we already had our I2 cells dying. That was our equation E5. But the rate of death was independent of anything else. Now what you're going to have to do is add an additional death process where you have this functional form. Algebraically, it's a bit of a mess because you have to do multiplication and division, so you need some parentheses. But you're adding it to that equation E5, which is the death rate. So the immune system will show up as a faster death of infected cells. So the next exercise is basically to implement this death term in the basic model. So I'll give people a minute or two, a few minutes to try that out. And this ultimately is the whole point of all of this complicated modeling of the immune system. If the immune cells don't kill the target cells, then nothing is very interesting. I should say, and then maybe it's sort of discouraging, that we're oversimplifying in a number of ways. As I mentioned repeatedly, we've left out the fact that the immune cells, the antigen-presenting cells, and the T cells send out cytokines themselves. And so that C cytokine level should actually be increased by the presence of these cells. Another thing is that the antigen-presenting cells, which we haven't modeled separately from the cytokine, are primarily stimulated by the death of the infected cells. And so instead of having the seed signal be determined by the number of infected cells, it probably should be determined by how many cells are dying. The third thing is that the immune signal, we've modeled a positive feedback where the immune signal is turned on, but the only way our immune system was turned off, signal was turned off, was by clearance of the cytokine, by the decay of the cytokine. In reality, there's a delayed anti-inflammatory signal, which are other cytokines that are turned on slowly to turn off the immune response, to prevent overactivity of the immune system. And when people treat COVID-19 with dexamethasone, that's what they're doing. So dexamethasone damps down the immune response. People have also tried doing the opposite. They've used interleukin-7, which is supposed to make that the immune cells, the antigen-presenting cells, get to the lymph nodes a little faster, to try to speed up the immune response early on. And so from a point of view of treatment, it's rather complicated. Ideally, you want the immune response to be as fast as possible and as strong as possible early on. And then you want it to shut off as fast as possible once the virus is eliminated. If you give dexamethasone too early, you have the risk of suppressing the immune response, in which case the virus can infect too many cells and you die from the virus infecting the cells directly. If you give it too late, it doesn't do enough. And you might as well not give it. And so one of the things you'd like to be able to do eventually would be to be able to model each person's individual immune system and be able to determine when you'd want to enhance the immune response with something like interleukin-7 and when you'd want to damp it down with something like dexamethasone or another steroid that inhibits the immune response. In this model, we don't have an explicit anti-inflammatory signal. Now, we could actually have built a rather simpler model if we'd included that. It was probably a mistake in this model not to include the anti-inflammatory signal. Bard Ermentrout and Erica Mohan have been doing some nice modeling which have the pro and anti-inflammatory signals. And it actually behaves a little bit better than the model we've got here, and it's a little simpler. So in practice, implementing this one is pretty easy because it only changes one equation, which is here, which is that the death, the death rate of the I2 cells is increased. In this particular implementation, I typed it. Remember that equations in Tellurium add. And so if I have I2 goes to D here at a rate D times I2, I could either add here plus, oops, I could either go in here into this line E5, and I could add the killing rate DE2, EI2, or so on. Or I can put it into a separate line. And in this version, I decided to put it in as a separate line. Okay. So let's run that. What did people see when they ran it? What happened to the, finally, after all of this work, we should now have some effect on the number of infected cells and the amount of virus. What happened when we ran this? Anybody? People say they got it to work, so what happened? What happened to the amount of virus versus time? How did this change it? Well, do you think the amount, we can take a vote if you want. How many people say that the amount of virus stayed the same, that there was no effect on the viral load? Nobody. How many people said the amount of virus increased due to the immune cells? How many people say the amount of virus decreased due to the immune cells? Somebody can raise their hand or something. I'm not going to go on until somebody responds. You have to have some opinion about what happened. Okay. Goes down. When does it go down? Did it go down at day 2, day 4, day 10? When did it go down? How many people say that the amount of virus started going down on day 2? 2 people. How about day 4? 1. All right. How about day 6? Nobody. Day 8? Some people didn't vote.
I missed the
Nothing.
vote for 2.
You voted for 2? Okay. Well, maybe I did something wrong because when I ran it,
Define what you mean by the level of virus going down. Is like,
okay. So if we look before, maybe I wasn't clear, in which case I apologize. So what happened before, and I didn't give you parameter values, so it's not surprising if things didn't work. What I had before was that the amount of virus starts about 6 hours in. It peaks at day 2, it goes down gradually, and then it keeps going down gradually like that. That was what I had before. And all of this complicated game with cytokines, T cells, and everything else has been to replicate the fact that starting around day 7, the amount of virus goes down rapidly. And by day 9, the amount of virus is essentially 0. And I cheated a little bit because I did not give you the parameter values, although they were in the notebook. And so if you look here at the number of infected cells in the old system, notice the number of dead cells starts going up now early, and basically all the cells are dead. All of our susceptible cells have died after 7 days. which is not wonderful. It means that our immune system is controlling the virus by killing every cell in our tissue, which is probably not what we want. So maybe not such a great model. But let's go into this model here. Let's turn off the killing and see what happens. So let me turn the killing off. And here you see my virus comes up and then it decreases slowly at a constant rate. If I look at my number of dead cells, the number of dead cells starts coming up, but it reaches about 0.8 after 8 days. The number of infected cells is still pretty large at day 8. I'm now going to turn my immune response back on. Actually, the best thing to do probably would be to run these on top of each other, wouldn't it? So let's see, how can we do that? Why don't we do that together? I want to model this one time with the immune cells turned on and one with it turned off. So I'll do my load, I'll do my simulate, I'll do show equals false. Okay. I'll do m dot reset all. And then I will set m dot DEI2 equal to 0. And then I'll run this again. And this time I won't have it show false. Let's see where that works. I got that. Did it do anything? Reset all. DEI2 equals 0. Now let me change the color. I can't do that. Okay, so I didn't do the overlay, but I can see them next to each other. So this is the top one is the one with no immune system turned on. And the bottom one is the one with the immune system turned on. And so what's happened? The number of I2s is about the same. The early production of, the number of I1s is about the same. The early production of I2s, virus-producing cells, is the same. But then, starting around day 3, the rate of decrease of my infected cells goes down fast. The number of infected cells goes down fast. And the number of dead cells goes up much faster than it did before. And so basically, this represents the immune system coming in and killing everything. Whether you count that as a success or a failure, I'm not sure. If this were you, you would die if this is how your immune system responded. So maybe it's not a big success. But it does have the property that it gives the correct viral response. I guess the lesson there is that you can have the wrong biology up here, and still get the correct viral load curve. Let's see what would happen to the viral load curve. Same way if I do that. So I'm going to grab these guys here and plot the amount of virus. Same way. So now I'll plot the amount of virus. So this should now show me the virus in the two cases. So here's the viral load curve with no immune response. Sorry, the viral load curve with the immune response. Here's the viral load curve without the immune response. The maximum and the early response is the same, but starting around day 7, the virus cuts out, which is what I see. It's not cutting out quite right because it's cutting out because I'm killing all of my cells. It would be better from the point of view of the model if the system didn't kill everything. We could think about ways of making that happen. One way to do it would make the infectivity of the virus lower. But at least we're able to replicate the observed experimental curve. And then we can actually compare the experiment and the simulation. And they agree surprisingly well, especially given that we're killing everything, which is not really what's happening. We can ask the question, what parameter values work for this? We have to go back now to remember what we measured now 3 weeks ago, or 4 weeks ago from the experimental data. Namely, there was a delay of about 1/4 of a day, about 6 hours. There was a 10-fold increase every 1/6 of a day that went on for about 2 days. There was a saturation at a value of 10 to the 6th. At day, this says day 1, it should be 2. It's typed wrong. Then there was this slow clearance where the amount of virus went down by a factor of 10 over 5 days. And then there was this rapid clearance at the end when the amount goes down by 10 twice a day. Sorry, by 10 twice a day. And so that's what this is replicating. So let's see how we're doing on time. So there are a bunch of things that one could do. We're basically going to be out of time. We can do this as a little homework exercise. We can now try to do what I did by hand here, which is take this basic model, which we have, and change these parameters and see how these responses change. Something that we could do, for example, is that I'm killing all of my cells. I know that's not right, although it may not be such a terrible thing to put into a model of this kind to begin with. Because I could imagine modeling one tissue patch where everything gets killed and there's another uninfected patch that's left alone. But what would happen if I divided beta by 10? So I make the infectivity of my virus less. Well, slows things down. My infection takes a lot longer. Certainly slows the ramp up of my virus, but it doesn't rescue me. I still wind up with all of my cells dying. All of my cells get infected and all of my cells die. So that didn't work. And so it's actually sort of an interesting question, whether you could come up with a set of parameters for which the whole tissue doesn't die. And I actually don't know on that one. This model was built essentially for the sole purpose of replicating this viral load curve. And it wasn't explored in a great deal of detail. So there'll be a little bit of a homework exercise then to explore the parameter dependence of this model. Next week, the plan is that, Josh, did you want to say anything about fitting these parameters? No?
I mean, not in 9 minutes, no.
So next time we can do a little bit of fitting these parameters. So you can actually, we'll have for next week the experimental data available. And we'll actually start with these parameters that we had here and see whether we can actually come up with parameters that actually match the viral load curve to the experiment in detail. We'll be able to do that. And then, and we're still debating exactly which model to use, which is why we haven't given it to you yet. We'll try to do that by the weekend. We'll pick a different model, preferably one that is a little bit more biologically realistic, and we'll do what we did in class a couple of weeks ago, which is we'll take that published model and we'll replicate it together. So the kind of exercise we did a few weeks ago for the infection models. And that more or less should wrap up our work with in-host viral dynamics. And then we'll move on. See, that'll be lecture 11. Leave us with not a lot of lectures. Remember, you guys are giving the last 2 lectures. You're presenting your results. And if you think about it, that means if we're in lecture 10 now, and you're giving lecture, we have 16 weeks. So you're giving lectures 15 and 16, which means we have 11, 12, 13, 14, 4 weeks. So in 5 weeks, you have to be ready to present your projects. So it doesn't give us a lot of time. That's why I've been pushing a little bit to try to make sure we stay on target for getting the projects going. But we'll move to pharmacokinetic modeling. You're not going to be able to do it very much with it, but you'll get a flavor for trying to understand the question like, if I take remdesivir, what is the amount of remdesivir in my body as a function of time? When I take a pill, if I take a Tylenol or an ibuprofen, I don't immediately have my headache get better. The pill has to physically get from my mouth into my gut. It has to dissolve. The molecules in the pill have to get out of my intestines into my bloodstream. They have to be transported to the target tissue. Then they have to get into the target tissue. In the case of a molecule like remdesivir, which is an antiviral, used as the only drug that's really approved for use for COVID, the molecule itself, the remdesivir, is not the active compound. The active compound is actually a metabolite. That's not even the first metabolite. It's a couple of transformations down the metabolic chain. So what happens is with remdesivir, it's injected, so you don't have to wait for it to get into your gut. So it's put into your bloodstream, it circulates, it gets into your cells, including the infected one. And then there are a series of enzymes that transform the prodrug, the remdesivir itself, which is a prodrug which doesn't do anything to the virus, into the active form. And it takes some amount of time for that to happen. And the drug itself is cleared. It breaks down chemically, and it's also gotten rid of by the cells. It's also cleared by your liver and your kidneys. And so the drug has a lifetime in your body. So when you take a drug, at first there isn't any active drug in your cells, then it begins to ramp up, and then it reaches a peak, and then it clears and it'll decay again. If you take the drug once every 24 hours, and the ramp up time is slow, and the decay time is fast, then what you get are spikes of the drug, and a lot of time when you effectively have no drug, in which case during that period the virus can replicate. And so dosing schedules are an issue. You notice that some drugs you can take once a day. Some drugs they say take every 8 hours, some drugs every 12 hours. That has to do typically with how long the drug stays in circulation in your body. There's some drugs like Prozac, for example, that are very, very slow acting. They take days to build up, and then they stay present for a long time. There are other drugs which get into your body very quickly. It depends a little bit on how it's delivered, whether it's injected or oral or inhaled. And some drugs are cleared very quickly. That may be what you want, or it may not be what you want, depending on the mode of action of the drug, the toxicity, and things like that. And so we'll do a little bit of trying to understand some of the basics of how that works. Okay. So I appreciate, again, your patience with my losing my voice a bit today. But I hope that gives you something to play with. Josh and I will work on writing up. We didn't know exactly how far we'd get. We'll work on writing up an exercise or two for you for this. Again, your main assignment is to keep working on your projects. Please, if you have any difficulty with the homework assignment that was due today, come to me or to Josh, because it's critical that you be able and comfortable doing the things we've been doing, which are translating back and forth between diagrams, equations, and code. And with that, and if there are any questions about anything before we break, people, I know that's always a hard one. At 8 p.m., people are probably exhausted and want to have dinner rather than ask questions. But you're welcome to, colleague, go ahead, please. I didn't mean to cut off discussion.
I was actually going to ask just a clarifying question about how to draw the arrow diagrams, especially
Yes.
differentiating between like the different categories and then the reaction rates. So do you mind if I like annotate the screen for a second?
Please, go ahead. You should be able to do that.
So say we have like S
Yes.
going to I.
Mhm.
Maybe it's better to say like T going to E1, but like I guess it doesn't matter. S going to I. And then that conversion happens at like the rate beta. Actually, wait, let's just switch to the viruses. So we have T going to I1, and that happens at beta times V times T.
Okay.
Then this reaction, I guess, will increase as the concentration of both T and V increase. So do we replace this arrow with this?
Okay, so the arrow here, the first arrow that you wrote with a barb on the end, pointed arrow, says that the T cells become I1.
Right.
Which is what happens in this case. The lollipop arrow says that T promotes I1.
Oh, okay.
And so the second arrow would be saying that that T is not used up, so that the so the second arrow, if I drew the, here, let me see if I can get my, okay, so this is a really good question. Thank you for asking. So the second arrow, T lollipop I1, means the following. Certainly true, it means that more T means more I1, but it also means that T isn't used up.
Okay.
So instead of getting T dot equals minus beta VT, suppose that this rate were actually the same. Suppose this were BVT. T dot equals minus beta VT from here. I1 dot equals beta VT. The second equation would be true still, but the first one would not be true. This would be 0.
Okay. So then for the relationship between T and I, we still use this arrow, but say if we have V.
Right. So V is not used up.
Right.
So you could write, if you wanted to have a V arrow diagram, yes, exactly.
Okay. And then we wouldn't have to write any rate that goes along with that lollipop there. We just have it on top of.
Right. Yeah.
Okay.
That's right. Because V, basically you have a transformation, T goes to I1 at a rate beta times T, and it's being modulated by V.
Got it. Okay, that was confusing. So I was trying to do like the dashed arrows like we had seen before, and but then I was doing all kinds of weird things with like.
Well, I realized that I borrowed in a couple of places. I was inconsistent, having said that I would try to be consistent. Those dashed arrows are used a lot in these kinds of in-host viral models. They're not used in gene regulatory networks and signaling network notation. And so this was a problem where the different subfields have different conventions about how to draw it. And so some people are using the dashed arrow like this to be equal to a lollipop.
All right.
And then, I mean, they're not wrong. One has to be consistent. And so, as I mentioned, in Herbert's textbook, which we haven't really referred to very much this semester, although it's still a very good thing to be looking at, in the earlier versions of the textbook, almost every page had a different convention of arrows because he'd drawn examples from all sorts of interesting places, and each one of those examples used a different convention. And so now that textbook is very consistent in the way the arrows are demarked. They say the great thing about standards is there's so many incompatible ones. There are in fact something called biotapestry, which is a convention for how arrows should be drawn, which I'm basically following here. But like whether you write the T on top on the rate law or not, they're a little bit inconsistent about it. So that's a really good point, and I appreciate your catching that.
All right, that was all I had.
Any other questions before we break?
Yeah, Professor, would you mind answering a question about number 1 from the homework?
Number 1 from the homework. Do you want to screen share it so that I can?
Yeah, sure thing.
It's always possible that we have a typo in our homework too. So that would be embarrassing. But
I was really just curious as to whether these results look, I guess, on par with what they should look like.
well, Let's scroll up and see what the question was. Okay, so this was, let's see, Josh, you're the one who found this. This is one of Alan's models, isn't it?
I actually don't remember. Let me see.
So let's see. So we have nothing goes to X. So you have self-reduction. X dies, and relate proportional to X. That looks reasonable. X gets infected. That looks reasonable. Infected cells die. That looks reasonable. Nothing goes to the immune response. This is actually a better model than the one I just walked you through. Eta times Y.
Oh, this is the dengue infection model.
Yes. Yep.
Okay, so the question was, what is the actual time series supposed to look like? And so here, the amount of virus comes up, spikes at 10 to the 9th, and then disappears. So you get immune clearance. That looks all right. But let's see, uninfected tissue. Okay, so there's your tissue recovery too here, huh?
Mm-hmm.
So this is actually looks pretty good. The one thing, you have virus. So you've got virus plotted on both diagrams. That doesn't do any harm though.
Yeah, I just plotted the virus again on a bigger scale.
Right.
The first graph, so you can see kind of the intricacies of the other
Right.
concentrations.
Right. So you see, so X is the uninfected tissue. So you get the infection, you see, and then there's some recovery once the virus is eliminated. So that looks reasonable. Orange is the number of infected cells, and red must be the number of dead cells. Is that right? Is Z the number of dead cells? Can you scroll up?
Z is your immune response. And in the paper, it had a negligible immune decay, so they didn't include it.
Okay, so once it's there, it stays there.
Right.
All right. Okay, I mean, everything you've got here looks reasonable.
Okay, I was just asking because
no, that's
C. You ask to basically have an event where it's an intervention, and basically it turns D from 1 to 0, and so all of a sudden no new viruses are being produced.
Right.
But placing it at 10 doesn't really do much because it seems like the virus is already kind of resolved at time 10.
Well, that's perfect. What if you put it at day 5? I saw.
Yeah.
What if you put it at day 2? So if you put it at day 2, basically there's a little bit, the virus only goes up to 800 instead of, what was it, 10 to the 7th or something like that. So basically you've actually, you've done exactly what we would like to do. You've done exactly the kind of model that people like Alan Perlson. I'd have to double check to make sure that everything you show looks fine. I don't see anything there that looks suspicious. It's always possible that there's a typo or a numerical thing so that the time series aren't quite what you'd expect. But what you've got there makes perfect sense to me, which is antivirals mainly work if they're given early. So if you were exposed to dengue and you started taking the antiviral on day 2, you wouldn't get sick. If you wait till day 5, why don't you put it back to 5? The nicest thing would be to do this as a parameter scan so you can overlay. If you do it on day 5, you still don't get sick because that line, that blue line of X means it goes down a teeny bit, but not much, and then comes back. If you do it on day 10, then you might as well not have given the drug at all.
Right.
Because the virus is already done.
Okay. Yeah, I was just confirming that.
Yeah, so your insight is a perfect one, which is when we said to give the drug at day 10, it doesn't have any effect at all.
And to be fair, I did not run the model, so I did not know exactly what ranges were appropriate. But yeah, that's good.
No
But you
problem. Just making sure.
definitely get extra points for noticing that didn't make sense. I appreciate that very much. Okay.
Yes.
Good
What I like
job.
to hear.
Okay. Anything else before we break? That was a great insight.
One last question on number 3.
Okay.
So I'm looking at the reported results table, the second graph, just graphing the total number of cells. To me, that looks like that's modeling the uninfected cells, the infected cells, and then the R labeled cells. I'm assuming, is that recovered? I think so. Maybe. I have to look back at the paper again. But with the initial conditions assume only given for T and V, then the model will just by default start everything else at 0, which means that when I look at my curve, I'm not seeing both the blue and black curves starting at the same point. I'm seeing the black curve starts at 0, then like spikes up immediately and then flattens out. Do we need an initial condition for any of the other cell types for number 3, or is that fine?
Let's see. So we start with uninfected cells, T, and you've got to start out with either some amount of virus or, yeah, so it starts out with some uninfected cells, 10 to the 11th, it's a lot, and some amount of virus, not very much. And you're saying that when you run this, do you replicate the top picture? The red and blue curves?
Yeah, I can replicate that just fine,
Right,
but the second, for the second graph, I can't replicate that black curve, which I'm assuming is, based on what I'm seeing in my graph, is cells in the R category. I can't replicate that because we're starting it at 0.
Okay. Yeah, it's true. It doesn't look like there should be any pair of anything that should both start at the same value. So it's 10 to the 11th. Sorry, you were?
Yeah, I was able to replicate it all right. I can share my screen.
Please go ahead. Yeah. Okay, so because that's the total. Okay, so that's the sum of the two.
Okay.
That's right.
Yeah.
Okay. So what we failed to do was label that graph. So we didn't say what was being plotted.
Yeah, we did not.
And so that was to be fair to Josh, the initial plan was to only show the top part of it, the red and blue one, and then we said, well, if there's a problem, it would be useful to show the time series for the cell types as well. But we neglected to include the label. So that was definitely our mistake. Thank you for catching that.
That makes much more sense now.
And Josh, if you can update that assignment to put that in, that would be great.
Yeah, I'll update to the on the timing of treatment, so people can try at least 2 or 3 different times.
But I understand that it can be frustrating if there's a bug in a homework assignment. But I want to say that I'm extremely impressed that you caught the bugs. Maybe in the context of a virus modeling course, saying that you caught the bugs is the wrong thing to say. It sounds like I'm asking you to get sick, but I don't mean to say that, but I do appreciate it, and I think I'm what happened. I'll tell you, this is, I don't want to take too much of your time because it's late. Part of what happened here was that the initial plan for this assignment was that we were only going to do the writing the values. In other words, we're going to say, take this picture, write the antimony string. Take this picture, write the ODEs. And we weren't actually going to have you run anything. And then we realized a little late in the game that if we didn't have you execute it, you had no way of knowing whether you had a result that made sense or not.
Right.
And so we then went back and asked you to run it. The original plan was that you were going to do this week, and then next week you'd run it. But we realized a little bit late in the game that it didn't make any sense to do it that way. And so people have run it and discovered that we had not been as careful about that perhaps as we could have been. So if people want an extra day or two to play with that and hand these in a day, Thursday, that would be fine if you'd like. If you're done, that's fine too. But if you want, if those corrections are important to you or were frustrating to you, by all means, take an extra 2 days and work on it. Then we'll update the homework assignment so that at least next year people won't run into the same potholes that you did. Okay. Thank you very much for bringing that up. That's great. Any other comments or questions? Did anybody find any more mistakes in the homework? And by the way, if the notes have mistakes in them too. I mean, the slides are new for the most part, and so there certainly are typos and things in the slides. When I go through the lectures, usually the day after, I try to fix any typos that I caught, and I'll repost them online, usually as given, which isn't really as given, but is as given and corrected. If you've caught any errors in the slides, or there's slides that are unclear, please let me know, and I'll do my best to fix the slide decks to respond to any mistakes you catch or any things that you ask for clarification for. And then I'll repost the slide decks with the corrections. So I do appreciate it when you catch those things. Okay, if there aren't any other questions, you've been very kind to stay late asking questions. I appreciate that. Please go get something to eat and get some rest. And if people want to talk about projects and things, email me and Josh. Josh has his qualifying exam Friday. So between now and Friday, he may be a little bit nervous and busy. But Friday afternoon, he will have passed his qualifying exam. So he should be in a good mood and available to help. But I'm always somewhat busy, but I will do my best to respond to questions and comments. The weekends are always pretty good for me. So if people want to meet with me on weekends to talk about projects, that's fine. You're certainly not obliged to meet on weekends, but I'm available.